Hey guys, welcome back to another Tutortopia video. So in today's video, we'll be going over the Laplace transform and kind of some of its applications into first order differential equations. So what is the definition of a Laplace transform? So a Laplace transform is just defined by this equation right here, where f of s is just the integral from 0 to infinity of some function of t times this decaying exponential term. Okay? Next, I'll be going over some examples of how to calculate this Laplace transform for given f of t's. And then lastly, I'll be going over how we use it to solve some first order ODEs. Alright, so since we have the definition already given right here, let's just go straight into some examples. So let's just say that f of t is equal to 1. So it's just a constant line, goes like this. Okay? So then we plug my f of t into our formula given up here, and we get integral 0 to infinity of 1 e minus st dt. We know that the integral of e to the negative st is just going to be negative 1 over s e negative st. We then evaluate this from 0 to infinity. So when we plug in infinity, we get negative 1 over s times e to the negative infinity minus negative 1 over s e to the 0. This term just goes to 0, and this term goes to minus 1 over s. So then we know that the Laplace transform, this is the symbol that denotes Laplace transform, of my f of t, which is equal to 1, is just equal to 1 over s. We also sometimes write this as capital F of s. Okay, so now for a second example, let's just do f of t equals t. So this function right here. So we have integral from 0 to infinity t e negative st dt. Okay, so we ask ourselves, how do we solve this problem right here? We notice that we have one function, a second function right here. So we do u du dv v. So now our u in this case is going to be t, du is going to be 1, our dv is going to be e negative st, our v is going to be 1 over s negative e negative st. So now we just plug that into our integration by parts formula. So we have uv, so that's t times negative 1 over s e to the negative st. So uv minus integral of v minus 1 over s times du, which is just equal to 1. And then we have dt. This integral is, again, relatively simple. So we get negative t over s e negative st minus plus, because we can change that to a plus, e negative st all over negative s squared. And then we evaluate this from 0 to infinity and get negative t over infinity e negative infinity plus 1 over infinity squared e negative infinity. So this term is just 0. So now when we plug in 0, we get negative 0 over s e to 0 plus e to the 0 all over negative s squared. And then since this is the bottom part that we're plugging in, t equals 0, we'll have a minus right here. So then we get Laplace transform of t is equal to 1 over s squared. Cool. So we know Laplace transform of 1 is equal to 1 over s. Laplace transform of t equals 1 over s squared. So now if you want to, you could also do a proof where t to the n is just equal to 1 over s to the n plus 1. Cool. Okay, so now one more example that I'd like to do is the Laplace transform of f prime of t. So just in general, how do we deal with an f prime of t since we're wanting to use this to solve differential equations? So we just plug my f prime of t into our definition. So integral 0 to infinity f prime of t e to the negative st dt. We then do our separation of variables since we have two functions. So we say u equals e to the negative st, du equals negative se negative st, dv equals f prime of t, and v just equals my f of t because the integral of a derivative is just the function itself. Okay, so now plugging this stuff into our integration by parts equation, we have u times v evaluated from 0 to infinity minus the integral of v times du. So I'm going to say f of t times negative s e negative st, and then there should be a dt right here. Okay, so now we can add this, and we notice something kind of interesting here. This is actually the definition of the Laplace transform of f of t times s, right? Because if we just plug in this to the original equation for Laplace transform, which was given previously, we would get this exact same thing right here. Okay, so now we ask, what is this term? So just plugging in our bounds, we get e to the negative infinity times f of infinity minus e to the negative 0 times f of 0. Okay, so now we assume that this term is going to go to 0. The main reason behind that is lim as x approaches infinity of e to the negative x times x to the n is always going to go to 0. This is because e to the negative x is a really fast decaying function. And we can see this by L'Hopital's rule. So if we take the derivative of this n times, we would get n factorial times e to the negative x times x to the 0. This x to the 0 is just equal to 1, so I'll replace it with a 1. And then we ask limit as x approaches infinity. Clearly this n is bound by some number, so we'll just call it a constant. So now we get e to the negative x times some constant as x approaches infinity. Clearly this is going to go to 0, so 0 times a constant is just equal to 0. So therefore we can usually assume that this term just goes to 0, so this term just turns to negative f of 0. So now combining this right here with this right here, we get the Laplace transform of f prime of t is actually equal to Laplace transform of f of t times s minus my f of 0. So using the notation above, where Laplace transform of f of t is defined to be big F of s, we get f of s times s minus f of 0. And this is going to be used in the future to solve our differential equations in the next example. Okay, so now let's use what we derived above to solve a pretty simple differential equation. So let's just say that y prime plus y is equal to 1. Okay, so the Laplace transform of y is just equal to s times, I'll say big Y of s. I always use this capital notation to like kind of make sure that I know throughout the problem in what domain I'm working in. So this is in like the Laplace domain, whereas a small y given right here is in the time domain. And then I know that the Laplace transform of y is just equal to y of s. Sorry, right here I forgot to add in the y of 0. And then we also have Laplace transform of 1 is just equal to 1 over s. Okay, so we apply a Laplace transform to our whole equation over here, so we can just think of it as applying it to each side. And we get s times y minus my y naught plus my y is just equal to 1 over s. Okay, so now what we want to do is get our y's to one side and everything else to the other side. It'll become apparent why we want to do this in a second, but I feel like I'll just show you first. So we just add this to the other side, and then we pull out a y. So we get y s plus 1 is equal to 1 over s plus y naught. And then dividing by this s plus 1, we get okay, so now we have this equation right here, and since we have our Laplace transform of y on this side, what we can do is now take an inverse Laplace transform of my y is just equal to my y of t by definition, and then we also have that is equal to Laplace inverse of 1 over s plus 1 plus y naught all over s plus 1. Okay, so now to solve this, we just check out a Laplace table. Okay, so now looking at a table of Laplace transforms that I found online, we notice this term right here. So e to the at has a Laplace transform of 1 over s minus a, where we can see a right there and right there. Okay, so this looks awfully familiar to this up here, on this side specifically. Okay, so now we say Laplace inverse of my y naught all over s plus 1 is going to be equal to y naught e to the negative 1 times t, right? Because this one is a minus down here, but we have a plus right here, so then that means that my a is equal to minus 1. And I could just pull out this y naught because we know that integral y naught, where y naught is just a constant, t, I can always just pull out this y naught. So whenever I have a constant like this in my Laplace inverse, I can always just pull it out and try to find the actual function, which in this case was this. Okay, so now we ask, what is the Laplace transform, the Laplace inverse of this term? So it's not quite as easy, and it's not really found on this table, but we notice that this bottom denominator is a multiplication of two terms. So we go back to our calculus 2, and we say 1 over s plus 1 can be written as a over s plus b over s plus 1. Okay, so multiplying this 1 over s on each side, we get 1 equals s plus 1a plus s times b. Okay, and now we just get this in a kind of good form that we want. So that would be a plus b times s plus a. Okay, so now we notice that on this side, this is equal to 0 times s plus 1 times 1. and this is equal to a plus b times s plus a times 1. So we notice that this a is going to have to match with this term, and this term is going to have to match with this term. So then we get over here that a is equal to 1, and then a plus b is equal to 0, which then goes to b is equal to minus 1, which then we get this term goes to 1 over s plus negative 1 all over s plus 1. Okay? And we actually know the Laplace inverse of both of these terms. This one is just given above. We actually derived it ourselves. It's just equal to 1. And this one, we just did the same as right over here. This is getting a little sloppy, but I don't know if we get the idea. So this is just e to the negative t. And now we add it with our other term, which was given from right here. And we get plus y naught e to the negative t. So then we actually get a final solution of our differential equation given by my y as a function of t is equal to 1, and then I'm going to pull this out, and then I have my y naught minus 1. Cool, so now we actually solved our original differential equation using Laplace transforms with a given condition of y naught equals y naught. Cool, so now we can see that Laplace transforms are actually a kind of cool way of solving differential equations. In this specific example, we solved a first order differential equation. And I almost think of them as like a puzzle. Like you have a table to where you can like easily take the Laplace transform, and then you have to kind of do algebraic manipulations to get it into a form where we can again use the table and then get your final answer, kind of like a puzzle. Alright, thank you guys so much for watching. Stay tuned for the next video in this series, and I will see you next time.